that's fine.
Yes, sir. Good morning, sir. Sir, I shared my doubts in PPT format, sir, for a better uh, in the form itself and the mails.
Okay. Okay.
Yeah.
Let me check.
Yes, sir.
Just give me a minute before it opens. Okay.
Sure, sir.
Okay. So, the questions which are given here by one of the participants is that what is the impact of pull-in voltage in low pass filter or LPF? What do you mean by LPF, by the way?
Sir, low pass filter only, sir. Yeah.
So, see, when you have a low pass filter which is passive in nature, in that particular case, that passive loop filter is not going to change your pull-in voltage at all, or it is not going to restrict your pull-in voltage on either side, positive or negative side. But in case you are using active loop filter, using op amps and other things, right? So in that case, if you want to have some pull-in voltage for the PLL to lock, the active loop filter, based on its operation, it can always put a limit, and those limits may not be the supply limits which you have in the PLL.
Okay.
Is it like this, or is it something else which you are looking at?
Yeah, like this only, sir. Exactly. And sir, in before going to low pass filter, while moving to active filter, right? In low pass filter, you tell about the lower limits, right? Where it cannot go beyond even sine is magnitude is 1. It cannot go beyond -1/2 +1/2. So
No,
when it
okay, hold. So the thing is, if you exactly talk about the low pass filter, it doesn't limit anything. What is being limited is that, okay, because your mixer output, if you are using a mixer based phase error detector, your mixer output is limited by plus minus half or whatever amplitude times the sine. That is the limit not imposed by the low pass filter. That is the limit imposed by the phase error detector, because its output can't go beyond certain limits.
okay.
So the two limits are different. So I can have some other phase error detector with active loop filter where the limit is put by the active loop filter, or I can have a mixer based phase error detector and a passive loop filter where the limit is put by the mixer based phase error detector. So who is limiting it? That depends on the block which you are using.
Okay. Oh,
Uh,
okay. Yes, sir. Yes, sir. And sir, one loop filter, yeah. So that when once pull in voltage, I mean, when it comes to that is the reason why you are moving to active, no, sir. So when we are talking about in charge pump, right? So in charge pump, we use passive low pass filter, no, sir. There that limitation won't come in because of the phase.
no, well. Now slowly you are moving to a different block. So now, what you are saying is that you are using a charge pump. Okay.
Mm,
Now, most of the time, the way I have shown in the circuit for the PLS is the charge pump is used with PFD, phase frequency detector, right?
yes, yes, sir.
A phase frequency detector does not put any limit on the output. Like the limit is like supply voltage. It's a pulse width modulated output. So then you have a charge pump and then the loop filter. Now, if you are using a passive loop filter, okay, and you are using a charge pump which is made up of transistors. In this particular case, because charge pump is made up of transistors, there is a certain supply voltage. So if you think you can get any voltage greater than VDD or lesser than 0, unless you use both positive and negative supplies, you will not be able to get that. So then you can say the limit is actually not pushed by the passive loop filter, the limit is put by the charge pump, because charge pump will anyways have a current source at the top and the switch at the top, and similarly current source at the bottom and a switch at the bottom. So there is a certain limit that the potential can go up or down.
Okay. So yeah,
So whenever we want to have we want to accommodate large pull-in voltage or voltages which are across the very near to the supplies, the first thing is first we figure it out with a open loop simulations, that what is the maximum and the minimum control voltage required for the oscillator to work. This is without any loop. So you just have an oscillator, you want to cover a certain frequency range, you say that, okay, I want this particular frequency range or not. Okay, so this particular voltage. So once that high and low voltage is defined, and if that high voltage turns out to be greater than the supply voltage, it will not work with the charge pump. Okay, so that voltage should be somewhat lesser than the maximum voltage, which is supply voltage, and somewhat more than the ground, 0 volt. So we keep these voltages in mind while we design a charge pump. We say that, okay, let us say, for example, we are doing this in 180 nanometers, 1.8 volt supply. So we will not design a charge pump where the output voltage required is 1.75 for the VCO, because that will be a really hard design from the charge pump point of view, where you have a current source and a switch operating only with the 50 millivolts of margin. Okay, so we can say, well, we can 1.8 volt, we can go up to 200 millivolts close to the supply, or 200 millivolts close to ground. So our operation range is 0.2 to 1.6. This is how any practical design will go. Now, in case, for example, you say, no, well, I need to have a 1.75. I don't think a source series charge pump can give you any of these charge pump can give you. And so then you go for, let us say, my charge pump output. But by the way, by 200 millivolts, maybe the charge pump which you have designed or which is existing, that cannot go even 400 millivolts down. So
that
then
depends on the,
yes. That depends on the design. So then you can switch to an active charge pump, and you say, well, the charge pump output will remain same. The op-amp output should be able to swing closer to the supply. Now, what kind of op-amp you employ there, whether it can have a full swing or it has some other thing, it has gain boost, supply boosted, and other stuff, you can do that. So it all, you can say, it is like block to block, you can say, dependence. Now, all these things are dictated by the VCO, what kind of voltages are required to make it work. Based on that, we redesign the previous blocks.
And basically, control voltage will decides the rest of the parameters, sir.
Exactly. What control voltage you need, that will decide.
Okay. Yes, sir. Yeah, understood, sir. Sir, and regarding till week 4 and phase detectors, you discussed about analog phase detectors and digital phase detectors, sir. So to understand these things in much more detail, what kind of modeling I should do, sir, to get more insights? I mean, same things in our company also, we are using some phase detectors. So to get to map things that you discussed in the
See, the thing is, unless you design it, it will be difficult to know the nitty-gritties of the operation. So I think whichever company you work, whichever process you are using, whatever frequency you want to have a PLL, you go and design these blocks, and then you will see what problems you can fix. The course is giving you what kind of ideal characteristics should look like, right? Once you put the transistors there, you will deviate from those ideal characteristics. Now, whether those ideal characteristics are okay or not, that depends on the design. So there is no one line that, okay, if you achieve this, it is done well. In some cases, some nonlinearities are tolerable. In some cases, some nonlinearities are not at all tolerable. Okay. So it's very much application dependent, design dependent, your output frequency desire. The best thing would be that you go and you start designing each block in the process where you want to have a PLL. Let's make the whole PLL work and see how much does it deviate from the your ideal calculation and other stuff.
Sure, sir. Yes.
Okay. You said I asked another one. Charge pump loop filter, low pass filter uses a low filter. It does not impact on pulling voltage. I didn't get this question. What do you mean by that?
I mean, the same thing that we discussed in previous thing, no, sir. I mean, I thought based on the phase detector, instead of phase, I thought that loop filter will decides the that pull-in voltage. Instead of phase detector output will decides the pull-in voltage, no, sir. I thought in opposite manner.
Oh.
Yeah.
Okay. Any other question which you have?
Yes, sir. Everything is fine, sir. Yeah, I will try to design in circuit level. I thought if I do modeling, I may understand. I mean, you
No, see, modeling is good for understanding to the extent possible, but your circuit nonlinearities and other things, okay, those things you will understand only when you design. So, we always say, well, we are treating here square pulses, no, for up and down and so on, all other clocks like with the PFT and other stuff. You go and design it, you will never get the square pulses. You will get always with the finite rise time and fall time, and those finite rise time and fall time for all the pulses, they will also not be like 0 to 100% straight line. They will slowly, exponentially, or sluggishly increase and then sluggishly actually settle. So these things will show you their effect in PFT and charge pump both. Okay.
okay.
How much more it is that is depends on how you design.
Okay. Yes, sir. Great, sir.
No. Okay. So next, let me just come back to this.
Sir,
Yes.
I have one question that
Yes, please.
where I can get the solution of the assignments and some more problem questions so that we can practice.
Aditya, solutions are something which I would not like to give, but if you have any specific query regarding any specific problem, you can surely mail us and ask.
Okay,
Okay.
sir. Okay, sir.
Quite often, when the solutions are floating around, people believe that they know because they know the solution, so they know everything. But it is something which one needs to work to find that, okay, why is this? Why am I getting a wrong answer? Or why it is so? So that is people are not doing it right. So we
Yes, sir.
normally say, okay, let's not give the solution. Let people try, and if they come up with a query, we will mostly try to resolve that all our best
Uh,
abilities. Okay. So even
okay,
if
sir.
yeah,
No,
even
I
if you
have
do some
some doubts, sir, that I have done process correctly or not, or
no, no,
so
okay,
one or two question I got wrong. Then I am thinking that how to get that correct. That's why
yeah,
I
yeah.
am
So
asking.
yeah. So Aditya, in such cases, if you find that your answer is wrong and
Yes, sir.
you know the procedure which you have done, you can independent, not on the whole forum. So other you don't want others to see your working. So you
Hmm.
can always share with us, and we will come back to you on that. Okay, we will tell you which step did you miss or which step you took wrong. Okay, and we will
Okay,
help you
sir.
with that. Yeah, with
Okay,
that.
sir. Sir, where I can get the some practice, some more practice problems?
Well, there are PLL books which are there, but the problem is most of the time these books are either highly mathematical or these books are highly research oriented. Okay,
Yes, sir.
so in either of these cases, it's like it doesn't help.
Yes, sir.
So the only way it helps is that okay, you go and you design it
Oh,
because you may understand that this particular area is not a very basic area of any analog or digital stuff is a little higher. So it's little complex. Okay. So
Okay, sir.
once you design it, then you know what are the problems. And then you can come to the modeling. So even if you look for the correct modeling of the PL, right, that
Yes,
would
sir.
be mostly existing in the research papers. And those
Okay.
research papers are later collected and put together by some of the professors, and that made the book. I think you may understand whom I'm referring to.
Yes, sir.
Okay.
Yes, sir.
So they will not have any problems
Mm-hmm.
to solve.
Sir, but
My
I
sug-
don't have any simulator like thing and any software which where I
no,
can
well,
design.
no, this is the two things. I think, well, don't worry about this. You have two things, two softwares, I think. Right now you have Python available
Yes,
with
sir.
you, right?
Yes,
It's a
sir.
free software. You can always do a behavioral level analysis about loop gain and all those things, right?
Yes, sir.
In Python. The next one which is available is free software is LT Spice.
Okay, sir.
Okay. LT
Hmm.
Spice, you can always design the PLL in transient time domain. You can always run it.
Okay,
Okay.
sir. Hmm.
Another thing, I think specifically for PLLs, there's a
Yes, sir.
software called CPP Sim. Okay.
Okay.
And the CPP Sim is a really good software where you can design the PLL. It's a free. You
Yes.
can design the PLL and you can look for all like very sophisticated figure of merits. Okay. A
Okay, sir.
sophisticated metrics, I think, actually, not figure of merits. You can choose to design the PLL. You can you can go from a simple PLL to a fractional and complicated PLL. It
Okay, sir.
is specifically for such kind of circuits.
Hmm.
It is by, you can just search, it is CPP Sim. It is by a person, Michael H. Parrott. Okay.
Okay.
It is not
Hmm.
Parrot, it is PRROTT.
Hmm.
Okay. So this guy is known to develop this and it's really good. You will find like some notes about using it also there. I have used it quite extensively during my research. So I think I don't think there is any problem with that. Okay,
Okay.
and the
Hmm.
documentation is also pretty good for
Okay, sir.
that. Okay,
Sir,
yeah.
then can you please provide any tutorial-like questions and if it
What
is
tutorial like question?
possible?
No, they no.
Uh,
Like what tutorial? I'm saying you can go and design the PLL and see the same.
okay, sir. Okay.
Yeah, so just try that out.
Okay, sir.
Okay. Okay.
Sir, just to appreciate, I mean, I just looked up this CPPPLL website. They have got some amazing PDFs and all these kind of
Yeah,
things.
I
I
know
mean,
that. That's why I'm telling you. These people
yeah,
are
yeah,
really. Michael
it's really
Parrott
good.
is one of the stalwarts of this area, man. So yeah,
Right. Sir, in this context, I had also posted that in the this link. So,
hmm.
by the way, hi, I'm Toshik. I think we had interacted before. I mean, in my over my MTech course like 2 years back.
Okay, okay. So did you take the
So I
PLL
didn't
course
get it.
there also and PLL course there also?
No. Because I opted for PMIC, I couldn't get a chance to cover PLL. Both were offered, I think, on the same time.
Okay.
Okay. So I missed it. So that's why I plan to take this at this time.
No problem. Tell me.
Yeah. So the question is, so do we later in the course or somewhere, as like most of, I mean, ongoing people were discussing, so shall we have one or two sessions where we kind of understand what are the different kind of simulations, I mean, apart from the regular transient simulation or loop analysis, like what we do when we characterize PLL, or what are the different specs that we measure for a PLL, or how we derive them from a system level or top level, and the derived spec for the individual blocks, and how we characterize them through test benches, or are there other simulations like noise or those kind of things?
Okay. This is a very heavily loaded question, okay? One and for all. So one thing is that in PLLs, when we talk about what are the specifications, It comes from the application point of view. If you are looking for something in RF, let us say you are looking for a wireless transceiver, maybe operating at 5 gigahertz. So someone has to provide the clock for that. Now, there will be a reference frequency, which will be told to you that, okay, this is the crystal which we will be using, and this is the frequency which we want. Now, what characteristics of that frequency is required? That should be coming from the whole RF chain simulation. Okay, so we cannot just say I'm designing a PLL standalone. I can define the specifications of the PLL, and it will be good for all of you. No, it can't happen. So based on your RF chain, based on the mixer gain, which will happen in the RF chain, the kind of spurious tones which you will have based on the nearby channels, based on your adjacent channel power rejection, and all those things, someone will come and give you the specifications for the PLL in RF. Okay, this is like one. Similarly, when you look for the clock which is required in ADCs, so how does the jitter and spurious tones of your sampling clock in ADC will affect the SNR of the ADC? Someone has to define that. Okay, so that modeling is another different modeling. People will tell that, okay, I need this much of RMS jitter with these many tones below a certain value. Otherwise, my SNR degrades by 3 dB, for example. Okay, so this is like talking about the clock requirement based on application. Similarly, you will have all your wired communication, whether it is your DDRs or it is Ethernet or it is PCI Express, right? In all these standards, the clock which is being used, based on the jitter of this clock, your final BER will depend. Okay, so then it is not done like, okay, I have this clock, so I will get this BER. No, I need the certain BER of 10 power minus 12 in the wired communication, and I need this frequency. So the maximum jitter which I can tolerate, random jitter which I can tolerate is so and so. So you design a clock which gives you the random jitter below a certain value. So this is how these specifications come in. Once the specifications are available, which means once you know I need to provide a certain output frequency with this much amount of jitter, this is my reference frequency, then you can do anything inside that your PLL black box. Okay, and you just need to provide that output clock. This is one part. Second part is what kind of measurements do we do on PLL and other stuff? Well, the standalone PLLs, normally you look for the voltage spectrum of the output clock, which means that you are looking for what are the tones references first, are there any spurious tones, okay, those kind of things. By the way, these specifications are coming from the application side, but when you are measuring, you'll measure for these. The second measurement which you can do, which you normally do, is the phase noise, which is like looking the phase noise power spectral density and find out what is the integrated RMS jitter. Okay, and then the third one is where you look for the time domain variations in the rising edge of the clock, which is looked on a scope. So this measurement and the phase noise measurement, they should actually corroborate with each other. And the reason is that in one case, you are just integrating in the frequency domain. And in the other case, you are just waiting long enough so that you collect enough samples for the rising edge. The difference is that because most of the phase noise analyzer, their mechanism of generating the phase noise is a down conversion using a mixer. Okay, so the bandwidth over which you integrate, that does not extend beyond a certain value. So it may be 100 megahertz. Okay, so and it depends on the mechanism which different companies, your testing companies, they are providing. So an ideal mechanism is use a really good oscillator on the machine, which is measurement machine, to down convert and then measure the phase noise. Sometimes what people have done is they do a very broadband ADCs on your input signal, and then they do a mathematical processing to provide you the phase noise. Whatever they are doing, the max higher frequency is something which is not captured. And this quite often overlooks the spurs which are available. Okay, sometimes it is only till 40 megahertz, sometimes it is 100 megahertz, which means if you are having tones anything after 40 or 100, those will not be entertained. So these tones are also taken into account when you are looking for the time domain. Now, in time domain, if you are looking at the same thing, you will get now again the software does the analysis on whatever kind of samples you are getting. It will give you random jitter, it will give you deterministic jitter. It's like you have the jitter data, okay, and then you do a post processing to find which is the random component, which is the deterministic component. Your spurs are mostly deterministic component, so it will provide you that. Okay, so these are the three main measurements. Now, what comes is basically power supply noise rejection. So again, depending on the application, you do a measurement where you apply some kind of sinusoidal waveform on the supply voltage, or either on the whole supply voltage of the PLL or on the critical blocks of the PLL, and you see how much deterministic tone comes out. Okay, so this is one measurement which you PSNR, power supply noise rejection ratio, which you will have, where you plot this value across the frequency. So this tells you the susceptibility of your PLL with respect to the supply voltage. Okay, this is then a fourth measurement. Fifth measurement, which is again not done in many cases, but is quite like required in some application, which is Allen deviation. And Allen deviation is a measurement of the stability of your clock over a long period of measurements. Okay, we do not talk about it here, but because the question is very broad. So Allen deviation is like measuring your phase noise at 0.1 hertz, 0.01 hertz, and so on and so forth. Okay, so as the temperature, as the operating condition drift, temperature drift, even if you're using the PLL in a controlled environment, right? You can have an air conditioning in your room where you're trying to measure 25 degrees, having 25 degrees Celsius, but even then throughout 24 hours, the temperature drifts. That is one. Another thing is the local temperature of the IC can also drift. Okay, so this measurement actually measures the lower frequency noise. So quite often you will see regular phase noise analyzers, they will not be measuring the noise below 1 hertz, and not surely in the range of 10 power minus 6 hertz and so on. So how much stability do you have in ppm or ppb or those kind of things? Allen deviation is a Allen deviation, and the other term is modified Allen deviation. Those are the metrics which are used to do that. Okay, so these are the measurements which normally you do on PLL. Application will define what you need. So it is that much different, like vary. Okay.
Okay, sir. Sir, just to follow up, so whenever we come to, measurements, related to clocks or something, we have this kind of phase noise or jitter measurements, which usually in PMICs or other domains we don't encounter because those are mostly transient or stability kind of simulation. Okay, so to understand this, generic question, to understand this kind of measurements, what is being measured, how to measure. So, firstly, do we have, will we be covering that in the course, or
No.
if not, are there, can you suggest good, tutorials or videos or something where these kind of things are discussed, like how to characterize things related to clocks or noise, jitter, phase noise analyzers, and these kind of things?
Okay, so one thing is we are clearly not covering how a test equipment is going to measure it. Okay, what we are covering is that this particular, you can say, simulation, okay, is going to give you either because I covered mostly two things here, or three things. I cover here the phase noise. I say, okay, this is how the final noise will come at the output. You need to look for the phase noise. You simulate for the phase noise if you want using PSS and P noise or other things. I think that part has been told in the course. But the course is not having any simulation, so it is up to the student or whoever is taking it that, okay, if they want, they can actually go and simulate it. So that phase noise is a metric which is used to characterize the clock, and how phase noise comes because how phase noise exists because of different components. That part is covered. But how, when you measure the phase noise in a test equipment, okay, what is the equipment doing behind it to measure the phase noise? That part is not covered, and that is not a part of this course at all. Similar thing applies for even the time domain noise or for the power supply noise rejection. So the theory that how it appears is there, how the instrument is measuring that is not there. Okay, this is one thing. Regarding any tutorial or anything where you can get that how do they measure, I would suggest, I think there are only very few big players who give the test equipment which can do a very high-end characterization. If you go through the application notes of their equipment, okay, they will tell you that. And some companies also, they do that. I think means I have read from the company's notes also, like I think Silicon Labs, SciTime, Analog Devices, Texas Instruments, right? So if there is any, you will find the articles from there that, okay, what does the jitter, how the jitter is measured, what are different kinds of jitter you have, data dependent, this and all that, how the ISPER is converted to the jitter. So those things are there in the company application notes. And I think they are the best resources for this. And if you refer to any particular test equipment, let us say tomorrow, just as an example, you say, okay, I want to purchase a test equipment from Rod and Shorts. Okay, they have some of the very good phase noise analyzers. Okay, like many other people. So I'm not this. I take a name of a company, that doesn't mean that company is the best or the other company is not good. These are just like, see, Keysight, Tektronix, Rod and Shorts. They are the big companies who provide the test equipments. Okay, nothing in the order I take the name. I want to be clear on that. So if you are looking for any equipment, you go through the data sheet of that equipment, that how much can it measure? What is the frequency range of measurement? What is the noise floor which it can measure? What is the lowest frequency it can measure? Can it measure Allen deviation or not? Okay, so you go through that, and then you see the accuracy of that. You try to relate their accuracy of this with any related to their sampling frequency which they are using. As an example, if they say we are measuring a 8 gigahertz of clock from the sampling scope time domain, we are measuring 8 gigahertz of clock, but the sampling speed is only 10 gigahertz or only for, let us say, 20 gigahertz. So using a 20 gigahertz sampling speed, how are you measuring a 8 gigahertz of clock is a question. And that too, if I'm measuring a 8 gigahertz of clock, I would be looking for a jitter in picoseconds. Okay, so ideally, it does not appear to us that how it can be done. So there must be some processing which they are doing inside. Okay, so those details you can always look in those application notes, or you can check with the company folks that how are you doing it. These are very technical details. Okay, so sometimes they can tell you, well, yes, we are, like, for example, I had a discussion with one person that you are saying your basically your accuracy is less than 5 picosecond. Okay, accuracy is less than 5 picosecond in real time means that you are looking for something sampling speed which is like 200 gig. So I said your equipment is not giving us 200 gig. It is much lesser than that, and you are saying you are giving a mean of 5 picosecond.
Yeah.
So then he said, yeah, that is right, but actually we are doing some kind of interpolation behind to get this 5 picosecond accuracy. This 5 picosecond accuracy is not the raw accuracy which we are getting from our sampling speed. From our sampling speed, it is lower. It is like first, but we are doing a mathematical processing or doing some interpolation in circuit or in signal processing to give you the 5 picosecond accuracy. And we will give you 5 picosecond accuracy. That's the reply which you can get. Okay. So when you buy an equipment, you look for all these things. When you want to understand that how this equipment is doing it, best is their application notes, talk to their application engineer or their tech engineer. They will tell you exactly how they are doing it. Okay, exactly. At least they will not tell you the secret sauce of the machine. Otherwise, they will be out of business. Yeah. But they will give you a broad mathematical stuff, or they will clarify, yes, there is some system which is doing it. And if you go and search around, you will find that. Okay.
Okay. Thank you, sir.
Yeah. So there are people. Yeah. Thalapasi, I think just hold for some time because I see some kind of questions which are typed out in the chat window. Okay. So let me take them.
Sure.
Yeah. One person is asking, if possible, can I give an open assignment non-graded on announcement page where we can design a PLL using open source tool by ourselves by giving specification provided by. Okay, if that is the requirement, I can very well provide it. Okay, no issues with that. But the thing is, you do that thing using open source. I would recommend that if you do not have access to multiple tools, please try and use CPPC. Okay, it's a very good forum. You have all the tools there. Okay, but yes, the kind of PLL specifications I will provide. Then there is okay. Dynamics of PLL locking with the sinusoid versus NRZ or RZ, how are they different? Well, see, in case of your sinusoidal, when you are using a sinusoidal-based phasor detector, and when you're talking about the dynamics of locking, if it is not the steady state of the PLL, okay, which means you are starting your PLL, powering it on, and all the voltages can be anywhere, to be honest, okay? So what will happen here is that you will see more nonlinear waveforms. In case of sinusoidal, you will see more nonlinear waveforms like the increase in the voltage at every step or the increase in the voltage of those kind of things. Okay. Those things you will see that they are actually very different when you are having an RZ or when you are having the sinusoidal waveforms. But once your PLL is in a steady state, which means your PLL is locked, and then you apply a small variation here or there, okay, small disturbance. The response of the PLL for the towards the small disturbance is going to be same for all PLLs. It is not going to be any different. Okay, if you maintain the same loop gain, same kind of bandwidth, you will not be able to make out whether this is coming from your sinusoidal mixer based stuff or it is coming from your PFT based stuff. Okay, so that's how you will see the difference in any locking. Okay, other one is in XOR based PD, how duty cycle affect the results. Can you explain that? Oh, well, Amarnath, I think why don't you just try with 50% duty cycle and non 50% duty cycle and draw those waveforms and see that when you come close to the duty cycle, how the waveform flips. Okay, showing that that this waveform clips is like drawing the waveforms and writing down the equations. I think you should do it. If you face any difficulty in your working, come back to me with the snapshot of your working and we will look at it.
Sir, am I audible, sir?
Yeah, you are audible.
Sir, regarding the first question which I posted.
Did you hear my answer?
Yes, sir. I heard, sir. But we have defined acquisition ranges like lock-in range, pull-in range, hold-in range for those sinusoidal-based mixers and based PLLs, sir.
Yeah.
We have not defined those acquisition range for these
Yeah, we have
NRZ.
not defined. No, yeah, we have not defined for that.
Yes, sir.
So,
Why so, sir?
so no. So hold here. So even if you are looking, see, the moment we said that your the concept that basically your, let us say, lock-in range we are talking about, you should lock within a 0 to 2 pi phasor and all those things, right?
Yes, sir. Yes, sir.
Yeah, and so this is lock-in, and then you have pull-in and acquisition. The thing is, the moment you are using a type 2 PLL, okay,
Okay, sir.
and
Yes, sir.
you are using a PFD. Why did we introduce PFD? We introduced PFD for the same reason that we are not able to detect the frequency error beyond
Yes,
a
sir.
certain value. So
Yes,
once
sir.
you do that, you will type 2 integrator with a PFD. Your basically acquisition range is infinite unless any other block limits it. This is one. Second thing is that when you, let us say, you talk about the lock-in range, which is like your phase error is exceeding 2 pi or not. Now, this can be worked out. Okay, I haven't worked it out in the this place, but you look for this that, okay, you start with the 0, you start with like the edges aligned, you start with the phase error and
Yes, sir.
check whether when you write down the equations for that, okay, whether you have a solution before the phase error is 2 pi. By the way, you look for it the moment you are having uh, type 2 PLL, which is like you are having an integrator, you always flock to a 0 phase error. Okay, now
Yes, sir.
this will be a very much mathematical stuff, as I am telling you. Okay, this maths can be worked out. In case of PFDs, it was easier. In case of sinusoidal.
Okay, sir. Yes,
So
sir.
if you work out the math, then you will find what is the lock-in. Sometimes it is easier to do the simulation and find the range rather than look for the mathematical equations.
Yes,
So
sir.
the idea to convey was that there is a mathematical background to find the lock-in, pull-in, and acquisition range. There are solutions which actually try to extend these ranges, okay, and
Yes, sir.
you can implement them. In case you want a mathematical equation for everything, they can be worked out.
Okay, sir.
Okay, yeah. So do not get into worrying that there is no mathematical basis for the PFT-based equation range. There is.
Yes, sir.
I think if you refer to the book by Gardner, you will surely find it there.
Okay,
because
sir.
they are one of the most mathematical, you can say, explanation which you will find.
Yes, sir.
Okay. So what is your other question? I think that was the first. And
in XR based PD, we have delved into the diagram of VPD versus pi error, sir. And we have defined those limits. What was the average of VPD in those ranges? But I don't understand how the function gets clipped before pi 2 minus d or after pi, sir.
Yeah. So Amarnath, just looking at the waveform will not make you understand that. Okay.
Yes, sir.
If you understand, that is great. But just looking at the waveform, if you do not understand it, that is not a problem at all. Please go and redraw these waveforms. You
Okay,
are having
sir.
an XOR based phase error, right?
Yes, sir.
You consider that your reference pulse, the one of the pulses is not 50% duty cycle. If you want, you can make it 55. You want, you can make it 40,
Yes,
whatever.
sir.
And shift the waveform to the right or to the left such that you are near the edge. And you then see how the XOR PD output change. Okay,
sir. Yes, sir.
in the presence of a duty cycle error. So this is something which you need to work out after drawing the waveforms and then writing down the equations for them.
Okay, sir.
Yeah. Okay. Anything else, Amarnath?
Sir, the third question is in charge pump based PLL. we have introduced a loop filter which contains a resistor followed by a capacitor in series. We state that the resistor acts as in proportional path and the capacitor acts as an integral path. Now in its nonlinearities or in its sources of nonlinearities, we said that this this resistor voltage is driving mad the VCO, so we get those reference bus, we need to attenuate it, so we put a ripple bypass capacitor. But this proportional voltage is the one which contains the information of the phasor at first, sir. Now we are attenuating it. Why so, sir?
Okay. So if you are having a phase error, right?
Yes, sir.
You want to integrate with both a proportional and the integral. You want to have both the proportional and the integral path that is fair enough, because you want the PLL to lock.
Yes, sir.
Okay. Now once your PLL is locked,
yes, sir.
your PLL is locked, tell me, do you still need a proportional path? Your PLL is locked.
We don't need it, sir.
Okay. So we don't need the proportional path to increase the voltage. Okay. But we do need a proportional path,
yes, sir,
for the stability of the loop. Okay. The problem is not that the proportional path is there. The problem is that because of the operation of the PLL,
yes, sir,
the charge pump has non-overlapping. The charge pump has overlapping region where the current sources both top and bottom are turned on, and
yes, sir,
they add delta current to the loop filter, though it is not needed. Whatever current is coming from the charge pump in the studies after the PLL has locked, during the overlapping period of up and down pulses, is not what is required for the operation of the PLL. It is an artifact of a mismatch between the top and bottom current source. So try to understand that.
yes, sir.
Okay. So
yes, sir.
Whom do you give the more weightage? Whether you retain this artifact that you are okay having a mismatch between the top and bottom current sources, live with it, or you try to actually minimize that effect. Because once you have a delta current periodically changing your control voltage of the VCO, then you are actually adding to the spur at the output. Okay. So this addition of spur at the output is something which is not good for the performance of the PLL.
Yes, sir.
Okay. So that is why we add a ripple bypass capacitor.
So but with
arguing it, just hold here.
Yes, sir.
Arguing it the way that, okay, you wanted to have a proportional path because you want to do a locking.
Yes,
but
sir.
now you are trying to minimize it. Well, what am I minimizing? I am not least. I am actually changing the order of the loop filters so that I filter out the or I suppress the component at the reference frequency effectively.
Yes, sir.
Not everywhere, not at DC. Right, not at a lower frequency. Well, lower frequency, depending on the loop filter bandwidth, I'm not doing, I'm still retaining that. But I'm trying to minimize the component at the reference frequency. And it is not in response to the loop behavior. It is in response to the added nonlinearity in the system. If you want to address the nonlinearity, there is no other way other than basically attenuating it. Either you attenuate at the source, which means you minimize the charge pump current difference. If you can do that, if you can make it zero, that is the best case. I will not be using a ripple bypass capacitor.
Yes,
okay,
sir.
But the thing is that you will not be able to do that. You cannot make that value as zero.
Yes, sir.
No matter what you do. Okay, this is
yes,
one.
Sir.
You want another thing? Well, you can add a notch filter there. Now, adding a notch filter at the because you know I am going to have ripples at the reference frequency, I will add a notch filter at the reference frequency. Well, if you can do it, great. But the thing is, adding a notch filter is more complicated than adding a simple ripple bypass capacitor. It's a trade-off.
Yes, sir.
Okay, so the thought that I am attenuating the proportional path, but I needed the proportional path for that. This is slightly taking you away. The correct method, or you can say a more straightforward way, is proportional path comes in first place because you want the PLL to lock.
Yes, sir.
Ripple bypass capacitor in second place because once the PLL is blocked in the steady state of the PLL, the reference, the charge from nonlinearities add current to it, so you want to attenuate that.
Yes,
So
sir.
you add another capacitor. That's how it is.
So that if those charge pump, the current sources in the charge pump are ideal and matched, we don't need that ripple bypass capacitor.
No. We don't need it. We will not even add it.
Yes, sir.
Yeah.
Sir, regarding the fourth question, I think doesn't make sense anyway. But I'm asking it in SR based PD. If we take the average of the up signal, it's equivalent to a PFD, sir.
No. In SR last phase PD, it's not like well. If you take average of the up signal, there is no down signal. Then how will you go for the negative phase error? First thing is that, like
Sir, please repeat it 1 second, sir.
If you are taking only up signal,
Yes,
you
sir.
are not considering the down signal, right?
Yes,
Then
sir.
how are you getting for the negative phase error? How is your output proportional to whether in magnitude or in sign proportional to the negative phase error? You have to take up minus down. Okay. Now SR based PD is not equivalent to PFT. Simple reason is because in SR based PD also
Yes,
you
sir.
are going to see both positive and negative outputs for a positive phase error. Okay, it is
Yes,
0
sir.
to pi. Yeah.
Yes, sir.
And PFD is not like that. PFD is positive for positive phase error, negative for negative phase error. There's a big difference there. You have seen the PFD characteristics, like that is going from minus 2 pi to plus 2 pi.
Yes, sir. Yes, sir.
Yeah, so it's a difference.
Yes, sir.
And then after 2 pi also, with the different frequencies, you can check that.
Yes, sir.
Okay. Okay. Where is the fifth question, man?
Fifth question, I think, how about guiding us through a design of a simple PLL using open source tool with some specific applications, sir?
But that fifth question is not stated here. Okay. See, you didn't get it. The joke. So the thing is, this open source, I told you, right? The CPP sim is the thing where you can design. Based on the request of
Yes,
the
sir.
people, I can actually post one assignment where you guys can try this PLL, okay, to see
Yes,
how
sir.
it works. That's fine. I can do that.
Yes, sir.
Okay. This
Sir.
guy,
Thank
yeah,
you.
just hold. I will come to you. Yeah, another question. In charge-based PLL, do we want a constant ICP which will vary slightly with PVT, or do we want an adaptive ICP which, for example, may vary with V control or some other parameters? Well, the answer is both yes and no. Okay, we do not want, if everything else is remaining constant in the PLL, we do not like KVCO, like loop filter values and other things, and the reference and other frequencies. We do not want the ICP to change, because change in the ICP will change the loop gain, and that is going to change the steady state dynamics of the PLL. Okay, that is one. So the answer is no for the, you can say the reply for no is that. The reply for yes is that in case you are varying the output frequency a lot, or you're varying the reference frequency because you're trying to have a wideband PLL, wide frequency range both at the input and the output. So in that particular case, you can argue that you need to vary the bandwidth of the PLL as your reference frequency is changed, or if there is a change in some other parameter in the PLL. For that case, you want to adapt the bandwidth. If you want to adapt the bandwidth, then changing the charge from current is one option, and you can exercise. So again, it depends on the application. Okay, what would you like to do? Okay. Yes, Saurabh, tell me. No.
Sir, I mean, in the beginning, you discussed about cycle clipping, linear settling, and tracking. Linear settling, no, sir. Sir, in our during our design also, where we see about settling importance.
You will see that, yeah.
So, I mean, how can I know? I mean, so what are the metrics for cycle clipping, linear settling, and all in PLL? So, what are the major contributors? Any reference papers to understand these things?
You can just put a rough search, right? Cycle clipping in PLLs. Okay, you will find the publication, and then there will be ways to detect the cycle slipping and to limit that. Okay, cycle slipping doesn't happen. So those kind of things, just type in Google, man. This is like, and
Yeah.
I believe if the AI at your back end, whatever you are saying is listening, it will start showing you. You open your Google Scholar, it will start showing you those results. Okay, so
Yes.
uh,
And yes, sir.
this is yeah, tell me.
Yeah, one more thing, major simulations will be done on RJ simulations, sir. In RJ simulations, we'll see that numbers, right? So after that, during our discussion, you explained about to measure the RJ. Oh, sorry, somewhere you told me about.
No,
During the discussion. Yeah.
I said that if there are dominant, RJ is the mostly the random jitter is the integrated noise which you get. That is because the random jitter, phase noise. But when you are doing a time domain simulation or you're looking at an eye diagram of the settled clock, right, it will have both the deterministic jitter also, which includes your reference spur, which includes your other fractional tones if there are. So uh, phase noise curves normally that doesn't have, because you need a little bit more processing. That doesn't have the your this thing, the spurious tones. So in order to see that, you only need to do a time-based simulation to do that. You can look at time domain simulations. The way is either you look at the voltage spectrum and you find that, okay, I'm having this much of reference spur, and this reference spur is going to contribute. See, reference spur is nothing but a tone. Okay, so then you say, okay, how will I convert this tone to a deterministic jitter? There's a direct conversion there from a sinusoidal tone riding over your required clock to the deterministic jitter, or you run the transient simulation, you look at you plot the eye diagram for the recovered, for eye diagram for the output clock, you plot it long enough to capture the jitter, which the spur which I am talking about, and then you will see the combined effect of it. You will not see any like, okay, deterministic jitter, it is one or the other. The combined effect of random and deterministic jitter if you are doing a transient noise simulation on your clock generator. There can be tools which can actually post-process the data and give you RJ and DJ.
Okay. Yes, sir. EMI simulations will also done to measure that spur only, sir.
Which one? Which simulation?
EMI simulations.
Electromagnetic interference simulation.
Yes, sir. Yes, sir.
On what?
To measure the spur of the clock. That is the utility of doing that simulation, sir. EMI simulation.
No, I don't think there is any direct requirement to do the EMI simulation on the PLL. So you are confusing between two things. You are confusing between the spread spectrum clocking, and which is normally done to reduce the electromagnetic interference caused by any clock generator. Okay,
Okay. Yes.
this is where the EMI simulations come. EMI simulations are not required in general from your PLL for your PLL. Okay,
Okay.
it is in a very specific case where you are worried about that you are generating a clock and there are other things nearby. You need to know that whether my clock generation on board or on IC, it is going to electromagnetically get coupled to the other signals nearby and degrade their performance. For that, you may be doing EMI simulations. Okay. And the solution to that is spread spectrum clocking, that you modulate your clock. You do not have one big tone at a given frequency. You just spread it around. Okay, so that is a separate thing. That EMI simulations is done not for the spurious tone. EMI simulations are quite often done for the main tone itself.
Okay.
It can be
Yes.
done for the main tone itself, and based on that, you come with the spread spectrum clocking. How much do you need to moderate?
Yes, sir. And RJ, regarding RJ simulations, sir, RJ is noise is the contributor for the RJ, no, sir. Can we, if in circuit level, if I'm trying to reduce the noise, does it has impact on RJ data, sir?
Directly, because Random jitter is coming from the thermal noise or the flicker noise of the components of each transistor and resistor. And if you reduce the noise coming from each transistor and resistor, then you will surely reduce RJ.
Okay.
Yeah.
For that, if I am trying to reduce the block level noise from current to to optimize level, it will directly result into RJ number.
Absolutely.
Okay.
Absolutely.
Yeah, sir. Sure, sir. That are my questions, sir. If anything required, I will. Yeah.
Sure.
Thank you, sir.
Okay, folks. I think I have taken precious 1 hour time of your Sunday morning. I do not want to waste more time for you folks. Have a nice weekend. Okay. I think folks at NPTEL also thank you for being available on my Sunday. We can disconnect now, and we will have our next session in the next month. Okay. Thank you.
Sir, if possible, can I get a next session within 2 weeks, sir? 4 weeks is a very long thing. We can cover more doubts within 2 weeks, if possible.
Well, 2 weeks in August and 2 weeks in September, 4 weeks. We will see. Don't worry about it. We will see when it is proper time. Okay.
Yes,
Yeah.
sir. More concepts are coming in upcoming discussion.
Sure.
We can.
Sure.
Yes, that's that.
Yeah. Sure. Okay.
Thank you, sir.